Okay, so we're going to continue with our work on the Legendre symbol. So quadratic residues and the Legendre symbol. Okay, so very quick 1 minute recap. Do I need to say that P is not prime? Yeah, I guess so. P prime, P is greater than 2. We've got our Legendre symbol. This is an indicator function. It gives you +1 if there exists an n such that n is congruent to n squared mod p. In other words, n is a quadratic residue. It's the residue that's left behind when you square something. It has the square root modulo p. All various ways of saying that. And -1 if it ain't so. Okay. And well, 0 if p divides n. But we don't really encounter the issue of it being 0 that much because we're normally focusing. I mean, if you're considering congruence classes modulo prime and the operation of multiplication, you normally don't bother considering multiples of p because they're all congruent to 0. And nothing much interesting happens when you multiply 0. You just get 0 all the time. There's nothing much to discover there multiplicatively about 0. But there is about all the other numbers. Key things we've discovered about quadratic residues so far. There are always exactly half of the non-zero things are residues, and the other half are not, are non-residues. Sentence doesn't quite make sense. P minus 1 over 2 residues and P minus 1 over 2 are not. They are non-residues. And we have that thing about the residues and non-residues mimicking the structural behavior of positive and negative numbers under multiplication. Multiply 2 residues, you get a residue. I said this at the start of every lecture. Multiply 2 non-residues, you get a residue. Multiply 1 of each, you get a non-residue. Or in other words, that was equivalent to saying that the Legendre symbol is a multiplicative function on ZP, on the multiplicative group of congruence classes under multiplication modulo P. The Legendre symbol, see I've just left the gap here for the first argument. You can think of it as a function on this, okay? Take an element from there, you put it in there, you get a value plus or minus 1. And it's multiplicative. That embodies that structural pattern of how residues and non-residues multiply together. The key theorem we proved. So there's the general problem that we're facing now is how to evaluate this thing. Given an arbitrary n and an arbitrary p, how do we decide if the n we're looking at is a quadratic residue mod p or is not? And we're seeking to discover what's going on, okay? Because of the examples we've looked at, we've seen, some curious behavior. Sometimes a number is a residue modulo some p's, and then it's not modulo other p's. And there's nothing obvious that's jumped out at us to explain why a thing is a residue or not, okay? Except in the case where the n is obviously a square, where the n is a square integer already, then of course it has to be a residue. But if n is not a square integer, it can sometimes be a residue and sometimes not. For some p's it's a residue, for some p's it's not. So there's this general problem of how to evaluate the Legendre symbol. Initially, we just used a brute force method. I mean, the systems we're looking at are finite. So when the prime is manageable, when it's a low prime we can think about, then we can simply square everything in the system. So you perform n squared for every n in the system, and then you'll discover which of the elements in the system are left behind as residues after you square them. Okay? So you can evaluate the Legendre symbol that way. But it's like brute force methods in general. It doesn't feel very clever. You're just kind of, machine gunning everything. It's not very exact. You're not kind of learning anything about the structure. And you're not just, if you do it on loads and loads of examples and try and look for patterns, maybe you'll see something come up. But we want to build on those examples and get something more definite. So Euler's criterion was our first step in that direction. And that told us that the Legendre symbol was always congruent to raising n to the power of p minus 1 over 2 modulo p. Now this is nice because it's like a formula involving n. It's all to do about multiplication, so you're raising n to a power. P minus 1 is the size of the system. Remember, there's p minus 1 non-zero elements there. And the fact that you're raising it to the power of p minus 1 over 2, so there's this multiple of a half there, that embodies the notion, that kind of, there's connections there with the notion of a square root. Something to the power of half is the square root. So the fact that you've got a half in the exponent is pleasing when we're talking about square root-like things, quadratic residues. Of course, this number p minus 1 over 2 is of course an integer, okay, because p is an odd prime, so p minus 1 is even, so when you divide it by 2, you do get an integer. Okay, so that's just a regular integer power of n. So where we parked it the last time was we finished with the proof of Euler's criterion the last time. In the tutorials last week, we looked at an application of it to the notion of generators for ZP. So if you're at the tutorials last week, you would have seen that. We discovered that quadratic residues can never generate the system because they're already squares. So when you raise them to powers, you effect only get even powers of its square root. So you're missing out kind of at least half the elements. We discovered that. We also saw that for primes of a special type that were 1 greater than a power of 2, we were able to use Euler's criterion to prove to ourselves that...
Sorry to interrupt.
You're right.
Is there a folder down there by any chance? Been left there?
What color is it?
Black.
Black folder, anybody?
Yeah.
There you go. Okay.
Sorry.
Okay. Good luck. Where was I before Folder Man came in? What was I saying? Oh yes, generators. Yeah, when P had that special form, when it was a prime number 1 greater than a power of 2, Euler's criterion, we were able to build an argument, a bit of a roundabout argument, but that told us that all the non-residues are definitely generators of the system. So that was nice to see. So where we're going to pick it up is looking at some more applications of Euler's criterion. And these are some nice evaluations. Some nice evaluations of the symbol. The first one we're going to do is theorem 8.5. Okay, so that was the end of the review, probably more like 5 minutes instead of 1 minute. Any questions, based just on the reviews? Also questions. Anything that people would like clarified a bit? Okay. Okay. Now, the way we're going to solve the general problem eventually of evaluating Legendre symbols, much like it's a bit reminiscent of the Euclidean algorithm. Remember the Euclidean algorithm? I don't know if in the versions, but the Euclidean algorithm, faced with the problem of getting the greatest common divisor of two large numbers, the Euclidean algorithm kept reducing the pair. You do all these integer divisions. You kept making the pair of numbers smaller and smaller and smaller. It was the same GCD all the time. And eventually the numbers got so small that one of them was 0 and the other one was non-zero, and therefore the GCD was whatever the non-zero one was. So that last non-zero remainder out of the sequence of integer divisions was the GCD. We're going to do a somewhat similar tactic to evaluating the Legendre P for general N and general P. We're going to reduce it. We're going to carry out, there's a way which we'll learn about called reciprocity, where we can flip the symbols. So flip an NP into a PN kind of. And because we know it's multiplicative, we can factorize the Legendre symbol. Based on the factorization of n, we can split it apart, and it's going to be the product of the individual Legendre symbols based on the factors in n. So we're going to have this reduction process that will reduce the Legendre symbol down to a product of a load of smaller Legendre symbols. So just as in the Euclidean algorithm, when we got one of the numbers down to 0, it was obvious what the GCD was the other non-zero one. Just like that, in tackling this general problem for Legendre symbols, we'll need to know, because we're going to be reducing the arguments in some kind of way, which we've yet to describe, we'll need to know about what the evaluations of this are for small values, for small n's. If we can get a couple of results together about how the symbol behaves for small n, then we can hopefully reduce all the symbols with the big n's down to ones involving the small n's and make use of those results. So this result is very much in the nature of that. And we're going to be evaluating minus 1p. Obviously, 1p always evaluates to plus 1 because 1 is always the square of 1. So 1 is always a quadratic residue. But the question is, what about minus 1? Or if you like, p minus 1. Okay? Minus 1 is congruent to p minus 1. So what's this equal to? Okay, well, the answer's in the statement of the theorem, but you can carry out some experiments to try and discover what the answer is. In a way, by just basically, you could use the brute force naive method of squaring everything to discover for a number of example primes what the value of minus 1p is. So we've got a Sage worksheet here. Just wait for the completions to load. But Sage has a built-in command called the Legendre symbol. The completions will load in a second. Probably. Maybe it has a lowercase l. Lowercase l. So Legendre symbol minus 1, 5. Minus 1 is a quadratic residue mod 5. It's not modulo 11, so you get minus 1. So we can try testing all the primes, say, between 3 and 50, and get it to output, get it to print P and the Legendre symbol. So these are all the values of the Legendre symbol, minus 1p, for every prime, for a whole bunch of primes between 3 and 50. So we might look at these and ponder this and see, can we spot any pattern, okay? Sometimes it is a residue, sometimes it's not. These are all the primes between 3 and 50. It's not too.
It's whether it's above or below a multiple of 4.
Yeah. It won't take you too long staring at that, looking for a pattern. I mean, the kind of patterns you're looking for. I mean, you might think of odd or even numbers, but of course these are all prime, so they all have to be odd numbers. Well, the next thing to think about is maybe, well, see, odd or even is thinking modulo 2. Well, the next step up in sophistication is to think modulo 3. I don't think there's a discernible pattern there, modulo 3, but when you think about it, modulo 4, everything that is one less than a multiple of 4, namely 3, 7, 11, 19, 23, etc., everything that's below a multiple of 1 below a multiple of 4 seems to be giving you -1. And everything that's 1 greater than a multiple of 4, namely 5, 13, 17, and so on, those ones seem to be reporting the value of +1. Okay. And I mean, you could test this out to 500. You would see that this pattern still continues. On and on and on. Okay. So it's a candidate for, it's a conjecture that, that you would fairly quickly arrive at just from studying examples. There's a definite pattern which we always observe based on the value of the prime modulo 4. Remember, primes, because they're odd numbers, they can only be 1 or 3 modulo 4. They can't be 2 or 0, because those are even numbers. So we have a definite candidate. So this is what the theorem says. It says it's +1 if p is 1 greater than a multiple of 4, and -1 if p is 1 less than a multiple of 4, which you could say is -1, but or 2. +1 if p is +1 mod 4, -1 if p is -1 mod 3 mod 4. And the proof of this is a straight ahead, no nonsense application of Euler's criteria. Okay? Couldn't be more glaring. There's Euler's criterion, a formula for NP. So that's what Euler's criterion tells us, that the Legendre symbol is congruent to -1 to the power of p minus 1 over 2. Now, not only is it congruent, see, the thing on the left is +1 or -1 by definition, but the thing on the right is a power of -1. So it's actually going to be equal to +or -1, not just congruent to +or -1, but actually equal to. So we can actually say something stronger. This is equal to -1 to the power of p minus 1 over 2. So it's not even something to do with a congruence modulo p, it's just plain equals. Now, if I give you a power of -1, how do you know whether it's +1 or -1? Yeah, to do it whether the power is odd or even. If you multiply -1 by itself an even number of times, it's going to come out as +1. Multiply itself by an odd number of times, it's going to come out as -1. Okay. So this value depends on the parity, odd or even, of the exponent p minus 1 over 2. Now, if p minus 1 over 2 is even, that means p minus 1 over 2 is equal to, say, 2 times n, some integer n. But that's equivalent to p minus 1 being equal to 4n, and that's equivalent to p being equal to 4n plus 1, which is, of course, congruent to 1 mod 4. Okay. Agreed? Whereas if it's odd, so you get a -1, that means you get a -1 for the Legendre symbol according to Euler's criterion. Well, if it's odd, that means it's equal to 2n plus 1, some integer n. And if you turn that around, that's equivalent to p being 4n plus 3, which of course is congruent to 3. So the exponent being even is equivalent to p being congruent to 1 mod 4. The exponent being odd is equivalent to p being congruent to 3 mod 4. So that's exactly the result that we're trying to prove. So that's good. We've established for one value at least, maybe for -1. The -1 is not a square integer, it's negative. But we've established a pretty good description of when and where -1 is a quadratic residue. The description is based on the congruence class of the prime mod 4. Okay? So like for a supergigantic prime, even for a supergigantic prime, it's very easy to tell what congruence class P is modulo. Like let's say it's, the prime has like a gazillion digits. What's its congruence class mod 4? Sorry? 1. Why? See, everything to the hundreds is, this is some multiple of 100, but 100 is already a multiple of 4. And of course, this number is equal to this n, or this p is equal to lambda times 100 plus 21. So if this is congruent to 0 mod 4 already, all you need to examine to figure out the congruence class mod 4 is just the last 2 digits. Okay, let's see what the congruence class of then mod 4 is. It's congruent to 1. So making this decision about what congruence class of prime is modulo 4 is not computationally expensive at all. It doesn't really matter how big the prime is, as long as you have access to the last 2 digits, as long as you've got access to the number itself, and you can immediately describe what its congruence class is. And that's, that's a definite step up from the general situation of Euler's criterion. The general situation of Euler's criterion would seem to require p minus 1 over 2 multiplications. So if you're dealing with a gigantic prime, that's still an awful lot of multiplication. So that, in general, you kind of might expect that to be a little bit computationally expensive. But in the case of -1, it's not. It's in a very limited range of values that -1 can move through when you raise it to a power, namely +1 and -1. We completely understand how it does that. Okay. So that's great for -1. We might, try and keep going. Theorem 8.6 establishes the same kind of result for the Legendre symbol 2 mod p. Now you can try the same game. I mean, thinking of how people discover this in the first place. So now we're looking at the Legendre symbol 2 mod p for every prime between 3 and 500. Okay, sometimes 2 is a residue, sometimes it isn't. Again, you think odd or even, you think mod 2, you think mod 3, you think mod 4, etc., etc. It turns out that the pattern that is there, the easiest way to describe it is considering the congruence class of p mod 8. So, it's not something you'd spot in a minute or two necessarily. It takes some patient consideration of it. But it's not that hard to imagine if you were gunning for these results in the early days of quadratic residue study and number theory. You spent your time studying, a substantial set of examples. Remember, these results we can discover by patiently squaring everything. If we square everything modulo 41, we'll observe that we do get 2 as a quadratic residue. If we square everything modulo 43, we'll observe that we don't. So, we can find these values by patient, thinking back pre-computer days, we can find these values by patient computation and studying them. It's not that hard to imagine that you could spot the pattern modulo 8. So it's the congruence class of the prime modulo 8 that determines whether the thing is prime related. It's if the number is 1 up or 1 down from a multiple of 8, so 7 is 1 down from 8, 17 is 1 up from 16. If it's 1 up or 1 down, you get a quadratic residue. The other possibility is that you're 3 up or 3 down from a multiple of 8, then you get a non-residue. So 19 is 16 plus 3, 29 is 32 minus 3. Those ones that are a distance 3 from a multiple of 8 are the quadratic non-residues. The ones that are right beside a multiple of 8, one step either way, are the residues. But that's not a proof, of course. That's we can see that pattern is consistent in the first few primes between 3 and 500, but it's by no means a proof of it in general. Okay, because who's to say that when you look at the next prime after 500, the pattern could suddenly break and you start to see something else. Okay. Plenty of examples. There's plenty of examples in mathematics of reasonably sound. Well, maybe not plenty, but there are enough of them around to cause you to be careful of what look like reasonable patterns that can be present in any number of initial examples, but that break after a while. Okay, so if we want to establish secure knowledge about quadratic residues, we require a proof. So that's what we're going to deliver. So it's +1. It's a quadratic residue if P is congruent to plus or minus 1 mod 8. You could also phrase that as 1 or 7 mod 8 if you wanted to, but it's kind of nicer to phrase it as plus or minus 1. And it's -1 if it's plus or minus 3 mod 8. Or you could say that as 3 or 5. Okay. And 1, 3, 5, and 7 are the only congruence classes modulo 8 of interest, because the other ones, 2, 4, and 6, they're all congruence classes of even numbers modulo 8. So if you're congruent to 2, 4, 6 modulo 8, you're definitely even. So you can't be an odd prime. You can't be one of our primes of interest. Now this proof is again based on Euler's theorem, but not so easily as the -1 case. Okay? So it's again based on Euler's criterion. Which said that the Legendre symbol 2 mod p is congruent to 2 to the power p minus 1 over 2 mod p. And the idea here is to obtain, it's congruent to this, so the idea here is to obtain this quantity, this power of 2, in a couple of slightly different ways. And then not equate them, but congruent them. So we're going to obtain the congruence class of this power of 2 in a couple of different ways. Okay? One way is multiply all the even congruence classes on P. That's what I mean by that. I mean, take all the even numbers. I think P is a bit large, so it contains 2, 4, 6, and 8. The last even congruence class you encounter is, of course, P minus 1. P is an odd prime. So P minus 1 is even. That's the last even congruence class. Multiply them all together. Because they're all even, you can take the factor of 2 out of each of them. So I can take a factor of 2 out of 2, leaves behind 1. Take a factor of 2 out of 4, leaves behind 2. Take a factor of 2 out of 6, leaves behind 3. Take a factor of 2 out of that, leaves behind 4. I'm going to put in an exponent on 2 there. But that's going to multiply 1 by 2 by 3, all the way up. As when I take the power of the factor of 2 out of P minus 1, you've got P minus 1 over 2. How many factors of 2 have I taken out? What's the exponent on this here? Well, it's 1, 2, 3, P minus 1 over 2. P minus 1 over 2. Okay. And this big bracket here also has a nice compact notation. Doesn't it? It's the factorial of P minus 1 over 2. Yeah. Okay, that's good. So if we multiply together all the even congruence classes, we get this power of 2. Euler's criterion tells us that that's the Legendre symbol. So now we want to do this in another way. So let's regenerate this product utilizing plus and minus signs. Now what do I mean there? Well, if I take the congruence class, this last congruence class that I used, that has an expression that's minus 1 mod P. This one here, 2, I'll keep that as 2. And for reasons which will become clear shortly, I'm going to say that's 2 times the square of minus 1. Then I'm going to take the one just before P minus 1 is, of course, P minus 3. Even number before P minus 1. And that's congruent to minus 3, which I'm going to say is 3 times minus 1 cubed. So start to see what we're doing. We're choosing them from the front and back of my list up here. What the hell, let's call that minus 1 to the power of 4. So it kind of feels a little bit tricksy, this, to be honest. So all these are congruence classes modulo P. You can't argue with any one of those statements, they're all correct. 4 is congruent to 4. P minus 5 is congruent to minus 5. Now, what will the last one here be? The last one here will be some congruence class S, which is congruent to, well, it might be plus P minus 1 over 2 or minus P minus 1 over 2. I'm not quite sure. It depends on the status of P mod 4, I think. Yeah, it depends on the status of P mod 4, whether the half of P minus 1 is going to be an even or an odd number. So I've got these whole bunch of congruences, and I'm going to multiply them all together. So I'm going to multiply all the left-hand sides together, and multiply all the right-hand sides together. Okay. Multiply all these together. On the left-hand side, you get, what are all these things on the left-hand side? These are all the congruence classes of even integers, modulo p. So that's that top line there, 2 by 4 by 6 by 8, all the way up as far as p minus 1. On the right-hand side, and this is good, what do you get? You got 1, well, so let's call this, fit that into the pattern there. When you multiply all these things on the right-hand side, you got 1 by 2 by 3 by 4 by 5, all the way up as far as p minus 1 over 2, which is, of course, your p minus 1 over 2 factorial again. That's when you multiply all these numbers. Now, you also got to multiply all these powers of 1. So you're multiplying powers of 1, so it's going to be a big power of 1. And what's the exponent here? The exponent is the sum of all these exponents. Yeah. When you multiply together exponents, sorry, when you multiply together powers, you add the exponents, don't you? This is 1 plus 2 plus 3. And the last one is p minus 1 over 2. That's a bit cramped there. Oops. Okay, so I'm multiplying together all those powers of 2. Okay, this is still, and the fact that we've got this p minus 1 over 2 factorial again is good, because we got that before, and it was multiplied by that, the power of 2 we need for Euler's criterion. And this is good as well, because here we're going to get that same factorial, but this time multiplied by a certain power of 1. Now, is there a better way that we can quantify this sum, 1 plus 2 plus 3, all the way up as far as p minus 1 over 2? Yeah. That's a non-threatening arithmetic series. Just adding up all the numbers, beginning at 1, 1 plus 2 plus 3, all the way up as far as some point. Okay, but you all know the formula for that. 1 plus 2 plus all the way up as far as n. That's the sum from j equals 1 to m of j. That's a half into m plus 1, isn't it? Agreed? It's just arithmetic summation formula. So you just apply that to here. So here the m is p minus 1 over 2. So it's a half of m, so it's p minus 1 over 4 times m plus 1. And when you add 1 to p minus 1 over 2, you get p plus 1 over 2. So you get the same factorial. Those multiply together to give p squared minus 1 over 8. Okay. So now we can equate our two expressions. See, because we multiplied together all the even congruence classes in two ways. One way we got this answer, which features the factorial and a power of minus 1. And powers of minus 1, you can easily figure out what they are. It just depends whether the exponent is odd or even. So that's non-threatening. Looks good. The other one We multiplied together the same set of numbers, all the even congruence classes. We got the same factorial, and we got the power of 2. The power of 2, which features in Euler's criteria. So when you, well, sorry, I say equate these, I mean, that implies put them together in an equation. I mean put them together in a congruence. Congruent. That's not really a verb. Anyway, 2 to the power p minus 1 over 2 times p minus 1 over 2 factorial is congruent to p minus 1 over 2 factorial by minus 1 to the p squared minus 1 over 8. Now, we're not interested in the factorials. They can disappear now. We're interested in this power of 2 because that's Euler's criterion says that that's equal to the congruent to the Legendre symbol. So that's going to be congruent to this power of minus 1, which we can analyze and tell whether it's plus 1 or minus 1. I want to just cancel those out of there. Now, this is a congruence modulo p. Think back to our early days studying congruences and divisibility. If this was an equation, for sure, you can cancel a factor from both sides, providing it's non-zero. We can do a similar thing with congruences. We can cancel a factor providing, what was the condition? You can cancel a factor away, providing it's co-prime to the modulus. Because really what you're doing is you're multiplying both sides by the multiplicative inverse of this factor. That will cancel it away and reduce it to 1. Okay. So is p minus 1 over 2 factorial co-prime to p? Why? Why are you nodding your head?
Because p is prime and p minus 1 is completely, and so that.
Yeah, p's prime. It has no factors apart from 1p. Here you're multiplying together a bunch of numbers less than p. This number has lots of factors. It's a factorial. They naturally have lots and lots of factors. But they're all small numbers smaller than p. And p doesn't have any small factors apart from the trivial 1, 1, which everything has. So p minus 1 over 2 factorial is definitely co-prime to p, because p is a prime. So we can cancel it. So that's equivalent to saying 2 to the power p minus 1 over 2 is congruent to minus 1 p squared minus 1 over 8 modulo. And this, in fact, is the Legendre symbol by Euler's criterion. So that's equivalent to saying the Legendre symbol, which is plus or minus 1, this is a power of minus 1, it's plus or minus 1, so it's now equal to this power of 1. And of course, powers of minus 1, you completely understand. It's plus 1, p squared minus 1 over 8 is even. And it's minus 1, that exponent, p squared minus 1 over 8 is odd. So the only thing we have left to do is just to understand the oddness and evenness of this expression, p squared minus 1 over 8. Okay. It's to do with the congruence class of this modulo 8. So just need to understand the oddness, evenness, p squared minus 1 over 8. See the table, page 61. I won't bother replicating this on the overhead. Here's p squared minus 1 for the various congruence classes mod 8. I'm only interested in the odd ones because p is a prime. So I don't need to consider the even ones. So just the odd congruence classes mod 8. This is the integer p written out as this is some multiple q of 8. You square it, subtract 1. Interestingly, they're always a multiple of 8, because the coefficients in p squared minus 1, when you substitute these expressions, they're always divisible by 8. So you do get this p squared minus 1 over 8 as an integer. And it's very easy to see which of these are odd or even, because the coefficients on the q are all even. So it just comes down to whether the remainder, the bit not involving q, is odd or even. So you got 0 and 6, they're even. 1 and 3, they're odd. So then we know the value of that power of minus 1. Plus 1 for the even remainders, minus 1 for the odd remainders. And you can track that back to the congruence class of p mod 8. And so when p is 1 up or 1 down from a multiple of 8, you get plus 1, so you get a quadratic residue. And when it's plus 3 or plus 5 or plus 3 or minus 3 from a multiple of 8, you get a non-residue. So see the table on page 61, which confirms the result. So that's nice. Again, it's a nice application of Euler's criterion. Again, it's a full solution now to the problem of knowing the Legendre symbol for 2, modulo any prime. Is that a tough ask to ask for the congruence class of a huge prime modulo 8? Is that a computationally expensive thing to do? Well, no, you can do a similar thing to here, except I'm not sure how far back you have to go. 10 is a multiple of 8. Each power of 10 is a factor of 2 in it. 8 is 2 cubed. So, 1,000 is a multiple of 8. Is that right? Must be right. I don't know what the other factor is. Yeah, but 1,000 is congruent to 0 mod 8. So all you have to do, if you want to make a decision about p modulo 8, is just look at the last 3 digits, okay? Because the previous bunch are all as a integer is congruent to 0 mod 8, and then you're just adding on this number between 0 and 1,000. And it's immediately, you can instantaneously know which of these are congruent to plus 1 or minus 1 mod 8, and which of these are congruent to plus 3 or minus 3. So just a quick calculation. Okay. So we've got really immediately available computational formulas for the Legendre symbol for minus 1 and 2. And they'll kind of form the basis, the bottom level, the basis level for our method of calculating any Legendre symbol. We'll reduce any Legendre symbol down effectively to those 2. Okay. So that's the kind of thing we're going to be discussing tomorrow. So I'll see you then. Thanks for your attention.